Before we can talk about the rational zeros theorem, we first need to understand what we mean by zeros of polynomials. Consider the following graph of a generic polynomial that we will call f of x. As you can see, it crosses the x-axis in a few places. These are known as the zeros of a polynomial. A zero of a polynomial is a value of x such that f of x equals 0. A fact that you probably learned in an algebra course but have since forgotten is that knowing the zero of a polynomial can help you to factor it. Specifically, if a is a zero of a polynomial, then we can always write f of x equals x minus a times g of x, where g of x is another polynomial. For example, consider f of x equals x cubed minus 3x squared minus 4x plus 12. A quick calculation shows that f of 2 is equal to 0. This means that f of x equals x minus 2 times g of x, where g of x is some polynomial. You might remember doing polynomial long division and solving for g of x at some point, but we're not going to focus on that part of the process. The important thing for us is that it is useful to know the zeros of a polynomial. In the previous example, we gave no indication about where the number 2 came from. We were just told that it works. The rational zeros theorem is a way to generate the list of all possible zeros that come from rational numbers. Notice the word possible. You will still need to check all the possibilities to determine whether any of them work. An important application of this is that if none of your rational numbers work, then the zeros are all irrational numbers. Theorem. Suppose C0, C1 up to Cn are integers, and r is a rational number satisfying the polynomial equation Cn x to the n plus Cn minus 1 x to the n minus 1 plus plus C1x plus C0 equals 0, where n is greater than or equal to 1, Cn is not 0, and C0 is not 0. Let r equal C over d, where c and d are integers having no common factors and d is not 0. Then c divides C0 and d divides Cn. The proof is just an exercise in algebraic manipulations. You should work out the details yourself just for the practice. We will start with the assumption that r is a 0, and since r is equal to c over d, we can just plug it in to get the following equation. We can clear the denominators by multiplying through by d to the n. From here, we're going to take this last equation and do two different manipulations to it. We will start by isolating the last term in the sum by moving everything else to the other side of the equation. Notice that we factored out a negative c from the right-hand side of the equation. The term inside the brackets is just an integer, so we have negative c times some integer is equal to c naught times d to the n. In other words, c divides c naught times d to the n. Remember that c and d have no common factors, which means that c must divide c naught, and that proves the first part of the theorem. To prove the second part of the theorem, we start from the same equation but solve for the first term instead of the last, and we use the same logic the whole way through. As an example, we will identify all possible rational zeros of the polynomial f of x equals 2x squared plus 3x plus 5. Notice that n equals 2, c2 equals 2, c1 equals 3, and c naught equals 5. The theorem states that if r is equal to c over d, then c divides c naught and d divides cn. In other words, c must divide 5 and d must divide 2. We can put this information into a chart that makes it easy for us to write down all the fractions. Since we have to consider both positive and negative cases, this gives us 8 calculations to do. We won't talk through it, but here's all the work. Notice that none of these is 0, so our equation has no rational roots.